So in the first part of this lecture series, we will learn about electronic spectroscopy, particularly UV-Vis Absorption Spectroscopy. So in this lecture, we will learn about the three major things. One is about what are the energy levels, or what kind of energy levels are present in the different molecules. Then electronic transitions in the organic molecule, and then molecular orbital diagram of formaldehyde as a representative example. So in the basic one is about in the first look we will learn about this energy level, and then we will talk about the molecular orbital diagram of the formaldehyde to understand these energy levels. So in the first run, we are going to study about the electronic energy levels. So within the molecule, there are two type of normally in this diagram we are presenting two type of energy levels, two type of electronic energy levels. One electronic energy level is called as ground state electronic, or the lowest electronic energy level, and this is the highest electronic energy level. So this electronic energy level is actually made up of small energy levels, and these are called as vibrational energy level. This one is a vibrational energy level. This is also vibrational energy level. So these are the vibrational energy levels. So within the vibrational energy levels, we have rotational energy levels, right? So from this diagram, we can understand the difference between the vibrational energy level, rotational energy level. Energy difference between the rotational energy level is smaller than the energy difference between the vibrational energy level. So it means if we provide energy to the molecule, so the very low amount of energy is required to change the rotational energy level, and as a result of this, molecule start getting rotate by absorbing that energy. And if we provide the energy equal or greater than the vibrational energy level, then the molecule would start vibrating on that energy level, but at the same time it start rotating at this energy level, because the vibrational energy level is greater than the rotational energy level. That's why if we provide energy equal to vibrational energy level, the molecule, by absorbing that energy, will also start rotating. And if we provide energy equal or greater than the electronic energy levels, then the electronic transitions takes place, and electron will be jumped from the first electronic energy state to another electronic energy state. But the energy that actually been involved in the change in electronic energy level is also involved in changing the both electronic, vibrational, and rotational energy levels. So electronic energy level have a high energy difference compared to vibrational energy levels, and then the rotational energy levels. So to understand these phenomena on electronic energy change and electronic energy level, we must know about, or to understand, the molecular orbital diagram of any molecule that will explain us the energy levels. So type of energy levels, and then we can assess, or we can explain that what kind of electronic transitions have been taking place in that molecule if we take its UV absorption spectroscopy. So here's a representative example of it, and this is a formaldehyde. So we are talking about the formaldehyde. Formaldehyde has a central atom that is called as carbon, and this carbon is sp2 hybridized, and it is overlapped, its orbitals are overlapped with a hydrogen, right? So hydrogen s orbital is actually involved or overlapping with the sp2 hybrid orbitals of the carbon. So likewise, this oxygen is also sp2 hybridized, and the orbitals of sp2 hybridized orbitals are also involved in overlapping with the carbon sp2 hybridized orbital. So here is sp2 overlap. In this case, carbon and oxygen, here is an sp2 spo2 overlap, while in the case of carbon hydrogen, this is ssp2 overlap. So here we have one of the orbital that is called as a px orbital of the carbon is actually not involving in any kind of bonding, whereas in the case of oxygen, one px orbital containing unpaired electron is also not involving in any kind of bonding, but it will overlap parallel to make a pi bond. So this will be responsible to make a pi bond, and this is actually the sigma bond. So this one is a sigma bond. Where there are two lone pair of electrons, one lone pair of electron is sp hybridized orbital and other is actually a py orbital. So it means in the formaldehyde, oxygen contains two lone pairs. One lone pair is sp and other lone pair is actually a py orbital, pure p orbital. So oxygen over here is sp hybridized and carbon over here is sp2 hybridized. So another detailed view, if we can take an example of this, if we have taken an example of this formaldehyde, so the formaldehyde contains a bonding molecular orbitals. This is pi bonding molecular orbitals and this is pi anti-bonding molecular orbitals. So in the case of pi bonding molecular orbitals, we're talking about pi bonding molecular orbitals. The bonding molecular orbitals are predominantly made up of oxygen 2p orbitals, whereas anti-bonding molecular orbitals are actually predominantly or enriched with the 2p orbitals. Right? So whereas it's lone pair, there are two types of lone pairs, and those lone pairs will be acting as a non-bonding molecular orbitals. One is actually a sp hybridized, another is a pure pz orbital, pz orbitals, and these containing two electrons, paired electrons. So whereas other are sigma bonds are between the two oxygen and the carbon atom. So it is a sigma anti-bonding molecular orbitals and sigma bonding molecular orbitals. So this is sigma bonding, this one is a sigma anti-bonding. So here we have an example of or simple MOT diagram of this molecule. We can see that the electron activity of oxygen is more than the electron activity of carbon. So carbon is less electronegative in the atom than oxygen. That's why the energy of atomic state energy level of oxygen is lower than the energy level of the carbon. When they overlap, we will get these type of orbitals, but we are talking about only non-bonding and pi orbitals. So bonding molecular, pi bonding molecular orbitals of this bond, right? We're talking about this bond. So in this bond, this is a bonding molecular orbital, this one is an anti-bonding molecular orbital, and this is non-bonding molecular orbital. So just within this structure of the molecule, it means within this bond we have two type of electronic transitions. One is pi to pi star, this is pi to pi star transition, right? And other was is n to pi star, non-bonding to anti-bonding molecular orbital. So definitely the amount of energy required for this electronic transition, that is pi to pi star, is greater than n to pi star, because the energy difference is more between these two. Energy difference between these two states is greater than the energy difference between the n to pi star orbitals. So here we already have noticed that there are two type of lone pairs on oxygen. One is actually a sp hybridized, another is only a pure pz orbital. So sp hybridized lone pair is actually strongly bonded to this oxygen atom, and that's the reason this lone pair is actually not involved in electronic transition. So if this electronic transition is allowed, then this sp hybridized orbital containing a electron pair will not allow that pair to get excited, whereas the orbital having a pz orbital having a 2 electron pairs is actually weakly bonded or less tightly bonded. That's why the electronic then transition will take place with this second lone pair which is made up of pz or a pure p character. So this would be the fundamental of this formaldehyde part, and then in the next part we will learn about the type of electronic transitions. Like one, we have 2 electronic transition we have noticed. One is a pi to pi star, another is an n to pi star. In the next lecture we will discuss all the possible electronic transition in the molecules, and then we will divide them into allowed and forbidden electronic transitions. Thank you very much.